Hello there. So this is section 4.2, video 2. So last section we introduced what is called the null space of a matrix. And remember we showed that sort of each matrix defines a subspace. Well, in particular, each M by N matrix defines a subspace of Rn in this way. And so this video we're going to look at yet another subspace that we can sort of derive by looking at a matrix called the column space of A. And so we're going to talk about it. We'll talk a little bit about some of the differences between column spaces and null spaces, but then we'll proceed very similar actually to how we did with the null space. So the column space of an M by N matrix A, where here I've defined it in this column notation, is the set of all linear combinations of the columns of A. So a more compact way of writing this, well, we might write COL of A. So this is sort of the abbreviation, much like we did for the null space, that we use to talk about the set that is the column space of A. And notice, by definition, it's just equal to the span of the columns of A, right? So remember that the span of a set of vectors is just the set of all linear combinations of those vectors. And so, this is sort of just another way of writing this definition, but a slightly shorter way. This will be very handy in a second here. But first, I want to just look at a concrete example. So remember with the null space, one interesting thing was that if we wanted to determine whether or not a vector was in the null space, it was a very quick check, right? Because all we needed to do was multiply A times that vector. And we're going to see here, and we'll see the reason why in a second when we start to relate this to sort of things we've already seen, that it's not quite as easy to determine whether or not a vector is in the column space of A. So as an example, I've got the same matrix we actually worked with last video. And so notice sort of if we were to look at this a little more concretely, the column space of A would just be the span of these four vectors. And so just one immediate difference that we'll talk about more at the end. So remember the null space of this the null space was a subset, and actually a subspace we can write, was a subspace of R4. Right, so remember that when we looked at the null space of this matrix, it contained vectors of length 4. But notice that here, the column space is a subset of R2. And we'll show in a second that the column space is in fact a subspace of R2. But notice the difference right off the bat, that the null space contains vectors equal to the number of columns of A, and the column space contains vectors equal to the number of rows of A. So, one difference right off the bat. So now answering these two questions is a little harder, right? Because remember, this sort of amounts to asking the question, does a linear combination of these vectors, right? Is this vector in the span of these vectors? And so notice each of these questions amounts to asking, does AX equal 4, 3 have a solution? And so notice that these questions are actually a lot harder to answer in the sense that we have to do a lot more work to answer them. Because notice what we're asking when we ask this question is this vector in the span of the columns of A, which is equivalent to the matrix equation AX equals 4, 3 having a solution. So sort of a second difference is that these two questions on their own are a little harder to verify for a specific vector. So sort of a couple differences right off the bat. The column space is a subspace of R2, or in this case, or a subset of R2, or in this case, Rm being more general. And determining if a vector is in the column space is actually a little bit harder than the determining if a vector is in the null space. So sort of just looking at this, you can kind of start to see a few differences. But one thing that, well, is sort of the same, they are both subspaces of the respective vector space that they live in. And so here is one of the main theorems of this video, that if A is an m by n matrix, then the column space of A is a subspace of Rm. So the proof for this is actually fairly straightforward given the theorem and the definition and what we already have shown to be true about certain things in the definition. And so I'll actually, for now, leave the proof of this as an exercise. I highly recommend you sort of read through the definition and try to think of a proof for this. Like I said, the proof for this actually really does just follow straight from the definition based on things we showed specifically in section 4.1. So I'll leave that as an exercise, but I will put the solution to that question of the proof of this theorem on the worksheet. What I want to do is, so we've got sort of this nice way of describing, I guess, all of the vectors in the null space. I want to sort of think about, okay, what do we know so far, or what have we learned in the class so far that can help us understand the column space better? And so I want to prove sort of a different fact in this video that will tell us a lot about the column space of A. And so we actually already observed this in the example that a vector is in the column space of A if and only if it is a solution to the corresponding matrix equation. So we say that a vector B in Rm is in column space of A for an m by n matrix A if and only if Ax equals B has a solution. So, we sort of saw from the previous example why this is true. Remember, we're just sort of asking, is this vector a linear combination of the columns of A, which we had already previously seen was equivalent to this thing having a solution. But we'll sort of prove it using slightly different method just to sort of confirm that this is in fact true. And so remember, because this is an if and only if, we have to show that this having a solution implies that the vector is in the column space of A, and the vector being in the column space of A implies that this has a solution. So we have two things we need to show. And we're going to start by assuming that the vector B is in the column space of A. What that means is we can find scalars C1 through Cn so that we can write B as a linear combination of the columns of A. But if we just let X be the vector whose entries are C1 up through Cn, well then AX equals B. And we've got that B being in the column space of A implies that there's a solution to this equation. And actually the other way is just basically this proof backwards. So if we assume there exists some vector x equal to, we'll say again, C1 through Cn, so that AX equals B, well then this means that, again, by expanding this, B is just equal to C1 times the first column of A plus C2 times the second column of A plus Cn times the nth column of A. And this implies that B is in the column space of A. So this was sort of just a slightly more detailed way of saying that basically all we're saying when we say column space of A is just the set of all solutions, or the set of all vectors in Rm, which this matrix equation is consistent, right? That is, has a solution. And so because of this, right, because of this fact, we actually know how to determine if a vector is in the column space of A. Kind of the first thing I'd introduced, that that question is a little difficult to determine, well, a little bit more difficult, but certainly not impossible, because all that we are secretly asking when we ask, is a vector in the column space of A, is, does the matrix equation AX equals B have a solution? And so we can look at one example of this with our favorite matrix of this section. You'd think since it was my favorite matrix, I'd have memorized its entries by now, but apparently it's not that high on my list of favorite matrices. So we want to let this matrix be defined, and we want to determine if the vector B, which is equal to 1, 2, is in the column space of A. And so now what we want to do is set up the augmented matrix and just solve the corresponding system of equations. And row reduce. And so we're going to do the same row reduction step we actually did in the first video. And so remember, this means we get the following system of equations with two free variables, x3 and x4. And so again, we just need to find some solution to the matrix equation AX equals B. And so maybe what we'll do is we'll let just both of our free variables equal 0. Then the vector x, -5, 2, 0, 0, is a solution to AX equals B, implying that B is in the column space of A. So as you can see, this problem in and of itself is maybe a little more difficult, in general, than the problem of determining whether a vector is in the null space But we've already built up the tools needed to answer this question for a specific matrix and a specific vector. So yeah, that's the column space. There's one more interesting problem with this that the book gives in relation to column space. And so I want to end with that example because I think it's fun, kind of a fun thing to sort of work backwards to do this, and then we will be done with, at least for the moment, done with column spaces. So we're going to let the following subspace of R4 be defined by, and what this is going to be is the set of all vectors that look like the following. So all vectors whose entries are 2s plus 3t, r plus s minus 2t, 4r minus s plus s, excuse me, and then 3r minus s minus t. And we're assuming that r, s, and t are all real numbers. All right, so what we want to do is find, and maybe I'll let this set just be equal to S, a matrix A, such that the column space of A is equal to S. So you could actually verify just sort of by the traditional 3 steps of subspace verification that this set is a subspace of R4. But notice if we can find a matrix A whose column space is basically the same as this set, well, then we have already shown that this set is a subspace of R4 because the column space of any matrix A is a subspace of the corresponding set Rm. So what I notice when I see this problem and how I want to do this, so notice that I could actually break this up into 3 different vectors sort of defined by each variable, right? And so then it's just going to be the linear combination of those 3 vectors. And so how I do this, translate this to a matrix, is I just assign a column of my matrix A. So what I mean by that is if X is in S, notice that means I can write X in the following way. And all I'm doing here is splitting up this one vector defining S into its sort of component parts of, oops, sorry, it shouldn't have S's in here. This should be just the coefficients. So notice I've just split it up into the component parts based on the variables. Well, and so what that means is that X is a linear combination of these 3 vectors. And what that means is that if I want a column space equal to S, well, remember, the column space of a matrix is just the linear combination of all columns. And so what I want is a matrix whose columns are just given by these vectors. And so notice here I ordered these columns in alphabetical order, but the order that these columns appear in actually won't matter, right? So I could have ordered these anyway, and the subspace generated, or the subspace spanned by these 4 columns would stay the same. So sort of an interesting fact, right, that 2 matrices that are the same, except for permuting their columns around, would contain the same column space. But anyways, that wraps up column spaces for now. And so we will move on to sort of how we can talk about linear transformations in the next video.